Welcome back to ECE 442-542. Wow, I guess it's not yet on the screen, but our next exam is a week from today. That will be on the screen as I scroll up, but I wanted to make you aware of a few things happening before then. Last time I think we talked about supplements for staying healthy. We're going to have some more for Unit 6. There's 3 different supplements, and they're not all 75 minutes. I think the last one on this special root locus is about 10 minutes in terms of the video. But homework number 6 is due on Monday, and the additional root locus material, there's one dealing with PI control with root locus. Obviously that one may not be applicable until maybe after today's, maybe even after Monday's, but I think you can watch it. The homework number 6 help, that might be useful now actually to watch that. That talks about open loop poles and zeros, closed loop poles and zeros, and how they are connected via the root locus. And then the special root locus video or notes is 2 real poles walk into a bar with a 0 to their right. I meant to say a restaurant. So 2 real poles walk into a restaurant and they have a real 0 to their 2 real poles to the right of 1 0. That's what I wanted to say. It's shown there on the diagram, and in fact, if you can't tell, if my X and Y axis were dimensioned consistently, then that would actually be a circle that connects what we will call the breakaway point, the point between the 2 poles, and that breakaway point is not necessarily equidistant between the poles. It actually is related to their distance from the 0, and it's a geometric mean. We'll talk about this later, or that's actually in the special root locus lecture, I hope. But it forms the circle is formed by putting the center of the circle at the 0. Once you've found the breakaway point between the 2 poles, now that's established your radius, and you can use that radius to draw the root locus branches that are off of the real axis. But you can see that there are a couple of segments of the real line that belong to the root locus, and on those segments are actually 2 branches. And hopefully it won't be confusing when we'll get all of this cleared up, but we will have a review session Monday night after our Monday class, and if you have questions or topics that you want included in that review session, you can submit those via the quiz on D2L. And as I indicated earlier, our next exam is in a week, exam number 3. Today what I want to do is get ready for that exam by giving you a quiz on root locus. We'll go look at some example diagrams, and maybe that's a little bit before putting the cart before the horse, but you can start to see what these root locus diagrams look like. Then we will just numerically calculate some roots associated with the characteristic equation, and that will be the closed loop poles. And we could, if you wanted to, if you were quick enough with your calculator, you could sketch a root locus by simply finding roots of a whatever order that is in your characteristic equation. Those points will belong to the root locus, and then we'll look at this idea of sketching root locus using generalized notation, and we'll finish with stating some, not all, of the rules for sketching a root loci. And we may not get to all of the rules before exam number 3, but we'll get to enough that we can do the problems that we need for exam number 3. Here's what we talked about last time. Root locus diagrams provide us with the closed loop pole locations in the complex z-plane, and those are going to be our branches of the root locus. And those closed loop poles are determined by the denominator expression in this closed loop transfer function, capital T of z. And that's 1 plus k g bar of z. And the values of z that cause that to be true for all these different values of k, we're going to go ahead and let k go from 0 to infinity. You plug in different values of k, that will give you the closed loop poles that belong to the root locus. And all of your root locus conditions or rules, well, we'll have two conditions, and all of our rules for sketching the root locus will be derived from or arise from those two conditions. The root locus conditions come from the closed loop dynamic equation, 1 plus k g bar of z. We solve that for k g bar, and we can do that by subtracting 1 from both sides of that equation. Minus 1 we can represent as having a magnitude of 1 and an angle of minus 180. And now we can look at the left-hand side and say we have two properties or conditions. We can satisfy the phase angle condition with this complex number on the left, and we can satisfy the magnitude condition with this complex number on the left, where the complex number is k g bar of z, and we're going to just assume in this class that we'll just restrict k to be non-negative. We won't worry about negative values of k in our sketches for the root locus diagram. That would just sort of confuse the issue, and we don't need to confuse it. We just need to learn the root locus. Once you've learned it, then okay, now you can throw the negative k in there and you can start to understand how that might change things. Here's the quiz. What is the angle? That's what I'm trying to show here. What is the angle of this transfer function g bar of z at a particular point in the complex plane, where that particular point is where I'm indicating by the triangle, the red triangle. That point is supposed to be at a value of 1/2 plus and minus, well, it's now just up at j 1/2. I've now located the two poles. One is at the origin and one is at z equal to 1. And now I want you to determine what is the angle of that transfer function g bar of z at that triangle location. That's the quiz. So can you find, and probably the more intuitive way to do it is to do it graphically or sketching, and then pull out your protractor. I'm sure everyone has a protractor somewhere in their pocket or in their backpack. Maybe it's on your phone. Maybe you have a protractor that just pops out of your phone, since everything derives from your phone these days. But you could, in fact, plug in or replace in this formula for g bar of z, you could replace both of those z's with 1/2 plus j 1/2 and solve it and find what's the angle associated with that complex number. If you do it graphically, and I didn't loosen up before class, so maybe I can use this to loosen up, because the angles aren't quite so big here, are they? Where the angles now, if you want to think about this physically, you could say, okay, I'm standing at these poles and I'm going to be pointing my face in the positive real axis direction. And now I have two. One is going to be a fixed arm. That's going to be the reference point, and then the other is a movable arm, and that measures the angle. And if I now wanted to know what is the angle contributed by that pole at z equal to 1 to get me to that triangle, I would just have to turn however far that is. And I think you can see, if my drawing was somewhat accurate, I'm really just saying there's the angle associated with that. Let me call that pole 1 since it's at z equal to 1. So I could now measure that angle. And I think you can see that if you just looked at the acute angle, a lot of times I like to take the acute angle and subtract it from 180, and that gives me the actual angle, theta p1. Here I have an acute angle that has an opposite side of 1/2 and adjacent side of 1/2. Oh, that's easy. That's 45 degrees. I take 45 away from 180, and I have 135 for theta sub p1. The angle associated with the pole at the origin is that angle. And now I don't have to, I can walk back to the origin, and now I just have to turn and look up to that triangle and find that angle, and it should be consistent with the angle that I just found on for the other pole, essentially. It's 45 degrees as well. What would happen, just to change things up a little bit, what if I put a 0 right there? And what am I doing? Now I'm saying, oh, I have a 0, and this would now be, let's say, plus alpha, or maybe I should call it z sub 0. This is now minus z sub 0. How would I incorporate that in my calculation of the angle for g bar? And how big is that angle? Just in very quick terms, is it bigger or smaller than 45? Smaller. And how does that incorporate into the angle for g bar of z? So now I'm just looking at this angle, and that would be my theta of z. Or in terms of looking at this, I would have a theta, see how I've already planned ahead? I have theta sub z minus the two pole angles, theta p0 plus theta p1. And whatever that theta z was would obviously influence the angle of g bar of z. We just calculated, or tried to say that these angles corresponded to 45, and this one was 180 degrees minus 45, or 135 degrees. So if I didn't deal with this, so that's not a pole, that's a crossing out. So I'm not considering theta of z in this formula. What's my angle of g bar of z at that triangle? The pole angles get subtracted because they're in the denominator of my expression for g bar, and I now have minus 180 degrees. And what does that tell me? That actually tells me that if I was sketching the root locus, my root locus would pass through that triangle, because that point has an angle or a phase of minus 180 degrees. That particular location belongs to the root locus. As I said before, if you wanted to analytically compute the angle of g bar at that point, you could plug in all of these, or compute algebraically these angles. We have 1/2 plus j 1/2. We have 1/2 plus j 1/2 minus 1. And if you wanted to, you could factor out the 1/2. And now that makes it look a little bit cleaner in terms of angle. You have up 1 and over 1, that's an angle of 45. You're back to the left minus 1 and up 1, that's an angle of 135. And I hope you can see that we now have 180 degrees in the denominator as an angle, which if you moved it upstairs, we have a complex number really of minus 2, and the angle associated with minus 2 is minus 180 degrees. And that's what would happen if we evaluated g bar of z at that one point in the complex xz plane. It would have a numerical value of minus 2, a complex number of minus 2, and we could find its angle as minus 180 degrees. So let's now look at some root locus diagrams, some example root locus diagrams. Again, we're not going to really say too much about how these arise, but this will start helping you to, I hope, sense what you might expect to see when you do start going through the rules for the root locus. The first one we've talked about before. We have one real pole. And why is the red line? We can do this because we know the angle of any point on the root locus has to be equal to minus 180. And now you can simply say, okay, I know that this root locus is on the real axis, but which side of that pole does it belong to? If you looked at this point and said, what's the angle from 2 to that red dot, I wouldn't have to stretch at all, would I, in terms of the angle? That's an angle of 0 degrees. So you know any point to the right of that pole does not belong to the root locus. But any point behind or to the left of that pole, now I do have to move through 180 degrees to get there, and I subtract those angles because they're associated with the pole, and now any point to the left of that pole at 2 belongs to the root locus. That's why the root locus just belongs to all points to the left. And what determines where I'm at to the left of that point will depend on the gain k that I've used in my closed loop feedback configuration. I can pick a k to put me anywhere I want from z equal 2 all the way to z equal minus infinity. I may not want to go that far. How far would I probably only want to go? Or do I even want to use a k? Do I want to just go ahead and live with this g bar? That g bar is open loop unstable. I probably do want to put some feedback around it, and I can now crank up the gain k to get me at least to the left of z equal 1, and probably not so much k to get me beyond z equal minus 1. Those are now my limits on the k that I would probably want to be living with, or between the lower limit and the upper limit. What about the root locus on the right? Now I have two poles, one at the origin and one at z equal to 2. And when I have two poles, and that's it, the root locus is pretty easy. We'll determine why it is the way it is, but we kind of argued a little bit to that effect in the earlier example when I asked, is this triangle on the root locus? You could now look at any point here. Wow, I don't know what that's supposed to be. supposed to be a triangle, or this square, or this cloud. But I hope you can see that those angles to get you to the triangle, the square, or the cloud are related in that the angle from the pole at 2 is shy of 180 by the same amount as the angle is at the pole at the origin to get you to that triangle, square, or cloud. So any point on that line, and what's special about that line is because it's halfway between those two poles. If it wasn't, then my angles wouldn't be related in the way that I'm suggesting they're related now. And that's true for any two-pole system. No zeros are present, just two poles. You can immediately sketch the root locus as connecting the two branches between those poles, and they will break away from the real axis halfway between those two pole locations. So now if I give you a two-pole system, a pure two-pole system, or you create a two-pole system by the appropriate choice of zeros in your controller or poles, you know how to sketch the root locus. That means that your closed loop poles live on those red branches. What about this particular one on the left now? The first thing you do when you sketch a root locus, if you want any kind of partial credit, is put down the poles and the zeros. The poles are the x's, the zeros are the open circles. Here we have a zero, a finite zero at the origin. That's pretty easy to locate. And the poles are pretty easy to locate. We have one pole that's equal to 1 and another pole that's equal to 2. Now you could, and we'll talk about this as one of the rules, but you can determine which segments on the real line belong to the root locus. And now I'll go back to what we talked about in the fall when we were cutting up our root locus into segments. We were chopping a piece of bread, weren't we? Had a loaf of French bread that was infinitely long. Now I'm hungry. But it went off to plus infinity and minus infinity. Imagine a piece of a loaf of French bread on the real line. And now you're going to cut that French bread anywhere you see a pole or a zero. In this case, how many pieces of that French bread exist for the pole zero diagram on the left? You have 4 different pieces. I might want one of those pieces more than another, but so be it. We now have 4 pieces of French bread. We have to figure out which of those 4 pieces actually belong to the root locus, which will be colored red. And that's going to depend on the angle being minus 180 at those segments. Meaning, if we look at the piece of French bread between 1 and 2, well, if we look at the infinitely long one to the right of 2, you can see that all the angles from the poles and the zeros are 0, so there's no way that that equals minus 180. We can throw that one away. That doesn't belong to the root locus. For those that have seen this before, you're going, come on, hurry up, hurry up. But the ones that haven't seen this, is it making sense? What I'm trying to suggest. I'm trying to shade the regions of the real axis that belong to the root locus, and now I'm saying that the region or the segment between 1 and 2 belong to the root locus. Why? Because the pole at z equal to 2 contributes 180 degrees. The pole at 1 contributes 0 degrees, and the 0 at the origin contributes 0 degrees. 0 minus 0 plus 180 gives me minus 180. Any point between 1 and 2 gives me that angle. You can argue similarly for the segment between the origin and 1. Now you have 2 poles giving you 180 each. Those add up to 360. The 0 gives you nothing. that angle anywhere between 0 and 1 gives you an angle of 360. That can't belong to the root locus. And finally, any point to the left of the origin has a 0 giving you 180 degrees and 2 poles giving you 180 degrees. And now one of those poles cancels the zeros angle, and you are ending up with minus 180 for any point to the left of the circle. So what's one of our rules? We've just derived it. We just need to look at each segment, each piece of this French bread that we've identified, and say, if I'm standing on that piece of bread, are there any poles and zeros to my right? And if they are, I want there to be an odd number of poles and zeros to my right. If I'm standing at 3, do I have any poles and zeros to my right? No. So that piece of French bread, or that segment of the real line, does not belong to the root locus. If I now step over and now I'm between 1 and 2, I say, oh, let's say I'm at 1 3/4. I look to my right and I say, how many poles and zeros do I have to my right? 1. 1 is odd. Oh, that segment belongs to the real, or the root locus. Now I go between 0 and 1, anywhere, 1/2, 1/4, and I look to my right. I see 2 poles. That's an even number, so that segment can't belong to the root locus. Finally, I go all the way to the left of all of my poles and zeros. Let's say I'm at minus 7, and I look to my right and I say, oh, I have 3 poles and zeros. That's an odd number. All of that from the origin to minus infinity belongs to the root locus. What happens off the root locus we'll figure out a little bit later, but in fact, this is the 2 poles and a 0 walk into a restaurant joke, right? Where these 2 real zeros lie to the right of one real, these 2 real poles lie to the right of 1 real 0. In that case, we have a circle with the 0 at the center of that circle, and we figure out the radius based on how far each of those poles are away from the 0. In this case, one pole is a distance of 1 minus 0. I'm doing the 0 for the location of the 0. It has a length of 1. The other one has a length of 2, and we actually look at the geometric mean of those 2 numbers. Not their average, but the geometric mean. So we're taking the square root of 1 times 2, or the square root of 2, the radius of that circle, determined by the center being at the origin in this case, is now the square root of 2 away from the origin. That's now this radius that we use to sketch the circle, and we re-enter the real axis, that radius away or to the left of that 0 at the origin. And hopefully I've sketched that somewhat accurately. Be a little bit forgiving, but we have a breakaway point between the 2 poles, a re-entry on the negative real line. What about the next root locus on the right side of this graphic or of this screen? Now we have more poles and zeros. We have 3 poles and a 0. And a lot of the behavior that we will be determining with these root locus, a lot of the big behavior will be determined by the pole 0 excess. How many more poles do we have than zeros, finite zeros? And here we have 3 poles and a 0, so the pole 0 excess is 2. We're going to see that what happens for large values of k is that these basically split the z-plane symmetrically, and the first angle of that upper branch is going to eventually approach an asymptote that has an angle of 90 degrees, or 180 degrees divided by the pole 0 excess. we'll get to that with some of the rules. But that's now, you could immediately, I hope, pull out your French bread and your knife and separate that French bread and determine which of those segments of the real line belong to the root locus by the odd poles and zeros. You can at least do that. Then we'll figure out what happens after that, after the breakaway, in a little bit. Here are a couple other pictures. I'm not sure why I didn't label the z-plane, but obviously I was tired when I was writing this up. But you can see that we have a 0 at 1/2, a pole at 3/2, and a pole at -1/2. And what's our pole zero excess? 1. So our asymptote will have an angle of 180 degrees divided by 1. What happens for large values of k are given by the asymptote angles. Here we just have one asymptote, so for large values of k, we're just going off to -infinity. And we have no action of our branches of the root locus off of the real line. That's a pretty easy root locus, as is the next one to the right. But do you see that I've put arrowheads or arrows? We start our root locus branches at the open loop poles, and we finish on the finite zeros, and we finish at zeros at infinity. And those zeros at infinity are at locations determined by the asymptote angles and what we will determine to be our centroid. We haven't gotten there yet, but we'll get there eventually. Those are some examples of root loci and how to, or what they look like. Now I hope I've motivated the need to answer this question. What determines the shape of the root locus diagram? I hope that those examples have now maybe piqued your interest. Maybe you're ready to pull your hair out. I apologize, but the idea behind showing you those diagrams was to try to motivate the need to answer or address this question. What determines the shape of the root locus diagram? Because we had multiple shapes up there, and we didn't even start to look at all of the different possible shapes. So let's look at this based on this example, and I'm going to call it example 2, where we have a G of Z, that's our open loop plant or system. It has a pole at the origin and a pole at 3/2. And we're going to use proportional feedback, or just a gain K. In this closed loop configuration, we have unity output feedback, and it's negative output feedback. We're comparing the output to the reference signal R, and that will produce an error signal, and that error signal now gets gained up with K before it starts driving the plant. And hopefully we can make this system stable. Initially it's open loop unstable. We have one pole at 3/2. Now what we want to do is, can we stabilize it and maybe achieve some behavior that's acceptable to us? And what we can do is we can sketch the root locus and say, oh, those red branches, do they simultaneously go through a region in the complex z-plane that maybe we're happy with? And what does it mean to be happy? Maybe it's satisfying particular performance specifications. Settling time, percent overshoot, and peak time. Maybe we can identify, you should be able to identify those regions, circles, wedges, or angles, and hearts, and how those overlap or intersect, and do our branches go through those regions in the way that we would like them to. Well, all of this for this particular example, we can find the closed loop transfer function. That's kg over 1 plus kg. We know g, and we're trying to look at what happens when we adjust k. What values of k do we use? We're using positive values of k, aren't we? We're going from k equals 0 up to positive infinity. And we want to see where are the closed loop poles for that range of values on k. You might be a little uncomfortable with this ratio of ratios. We can clean that up a little bit by putting everything over the same denominator in the numerator and denominator and canceling that, and we end up now with the closed loop transfer function being k over the original denominator polynomial z times z minus 1/2, I'm sorry, z minus 1.5 plus k. Now, fill in the blank. The closed loop poles are governed by what general equation? And it appears on the screen somewhere. What piece of this screen is going to produce our closed loop poles in general? So there's closed loop poles everywhere floating around, but what's the general formula? And it is 2 on that screen, or it's on that screen as well. What governs the closed loop poles? Point at it. Yeah, that'll make it clear. Point at it. There it is. Yeah, there it is. And if you're at home, you can point at it as well. But I'm really wanting you to write it down. It's the denominator expression, which is 1 plus k g of z, and we set that equal to 0. And we want to now adjust k through 0 to infinity and find out what values of z satisfy that equation. And it's really, when we look at 1 plus kg of z, that's some rational expression. It actually has a numerator and a denominator, but the numerator of 1 plus kg of z will determine the denominator of our closed loop transfer function. Can that be any more confusing? But if you think about it, the numerator of 1 plus kg of z is going to be the polynomial that will determine our closed loop poles. And for this particular problem, we've already identified that. Is it clear what I'm talking about? I'm talking about really the numerator that you find when you put the denominator over a common denominator. So you put that over a common denominator and you look at the numerator, and that's what ends up being that expression. Z times z minus 1.5 plus k. That's what I'm meaning by the numerator of 1 plus kg of z, setting that equal to 0. In our case, that's this z times z minus 1.5 plus k equaling 0. Or if we multiply it out, we end up with z squared minus 1.5z plus k equaling 0. Now, do you want me to tell you a secret? When I was in your chair, they did have calculators back then. I know, it's hard to believe. But there were calculators, and I actually had one that I could kind of program. And I programmed it to solve for the roots of that, and I kind of cheated on my root locus sketching. I knew that the root locus had to be the values of z that caused that to be true, so I'd just plug in different values of k, And boom, I could find sort of a locus of closed loop poles, and I could just connect the dots. Nobody said I couldn't do that, so I did. Shh. No one will know, right? So let's do that here. What happens to the roots of that equation with respect to changing k? When k is equal to 0, where are the roots? That's pretty easy if we just look at that middle expression. Z times z minus 3/2 equal to 0. So we have two poles. One's at the origin and one is at 3/2. So let's write that one down. We can do that. That's now z1 and z2. For k equal to 0, we have one at 0 and the other one at 3/2. And we can identify, or we can locate those. Boy, isn't this a nice picture? I'm just going to stand back and kind of enjoy this one for a little bit. I spent quite a bit of time trying to draw that, so I have to enjoy it. But we now have a pole here and a pole there. That's where we start. And now we can just start increasing k. And let's not go too small. Let's say we put in a k of 1/4. And in fact, did I do this? I can do that with a different calculator. I didn't have this calculator back then. No, that didn't happen. But I can do complex zeros to find the roots of this quadratic, and that vertical bar says with k equal to 1/4. And I'm trying to solve for z. And now it tells me where they're at. I have two real poles. One is about, well, it's at 0.19. I'm not going to be able to draw that very accurately. And the other one's at 1.3. For k, I've got a knob. I'm adjusting this knob k from 0 up to infinity. Maybe I don't want to go that far. But as I adjust it up to 1/4 and find the roots of that quadratic when k is 1/4, this is where they're at. And you could do that manually. You could just plug in the quadratic formula for this polynomial when k is equal to 1/4. That's all we're doing. And what did I just say? They were at 0.19 and 1.31. Like I'm going to be able to draw that much accuracy. But let's just assume that I can. Now I am here and I am there. So this is my square. So these two poles are moving, and if you wanted to, we already know which French bread pieces or segments belong to the root locus. It's going to be the piece between the origin and 3/2, based on having poles and zeros to the right. I made somebody hungry by talking about French bread, so they had to go visit the vending machine maybe. I don't know. Maybe not. Somebody went to McDonald's, looks like. Sure. Anyway. So now what do I want? Let's look at a different value of k. Let's not get too crazy with the values. Let's look at k equal to 1/2. And let me label that as a triangle. And if I did that, which I did, it's pretty easy with some calculators. You just copy that formula down again and then just remove the 2 and the 0.25 and hit enter, and boom, your answer's right there. 1/2 and 1. That's now where my closed loop poles would be if k was equal to 1/2. So this is now at 0.5 and 1.0. And if I'm now sketching with the correct shape, I now have my poles, and you can see maybe that those poles aren't moving the same distance on the right and the left. Maybe they are. In this case, they probably are, because everything is breaking away at the proper halfway point. But if you had other poles and zeros, the speed with which one branch point moves relative to the other may not be symmetric. Here it is, because our poles are symmetric and we only have two. So as we cranked up the gain to 1/2, now we're just on the verge of stability, right? We've just touched the unit circle, so that knob that we're adjusting stability of our closed loop system with, we have to get it at least to 1/2 in order for our system to be closed loop stable. Maybe I should do this. I know that I'm living here, aren't I? And I know that this guy is going that way and this guy is going that way. So let's pick another number, and I'm not going to make it too big yet. Let me make it 9/16. Just a little bit bigger than 1/2. And I'm running out of shapes, but let me make this an upside down triangle. And if I do that with the quadratic formula, k is now 9/16. I end up with, whoa, 0.75. Well, the calculator doesn't give me both roots for whatever reason, but I know that they're on top of each other. I'm now at 3/4, and can I just draw one symbol, even though you know that it's really two on top of each other? I'm now at the upside down triangle at 0.75. Now I am stable. So if I cranked up that gain a little bit more than 1/2, up to 9/16, now both poles are at the same location and they are at 3/4. They're both inside the unit circle. Now we're getting somewhere. What happens if we go a little bit more? Are they going to go whizzing by each other? No. They barely like to meet, but once they meet, they leave. They can't, 9/16 is a sweet spot, but after that you get above that and they leave the real line. They can only be on either side of each other, and then they're right together, but once they are above that with the gain k, they separate. And in this case, if I now said 3/4, that's now supposed to be a diamond. They are now at 0.75 plus j 0.43. Boy, I should have given myself more. I did on this one, didn't I? 0.75 minus j 0.43. These roots are going to be conjugates of each other. And you can see that they are fixed on that real distance, or on the horizontal distance equidistant between 0 and 3/2. They're at 3/4. And they're always going to be at 3/4 because this is our pattern, two real poles. So that shouldn't surprise us to end up with a real part of 0.75, and now our imaginary part is about 0.43. Did I draw this right? So let me... Oh, that's supposed to be a triangle, or I'm sorry, a diamond. So that now that's what our root locus is suggesting it's going to be. What happens if we plug in a k value of 1? That must be special, so I'll give it a star. What happens? Well, if we plug in k equal to 1, we end up with 0.75. That's good for the real component, and the imaginary component is 0.66. And if we looked at the magnitude of that, either one of those, you'll find, I believe, that that gives you a magnitude of 1 for those roots. So at that particular point for the star, we are right here. Again, right on the unit circle. This point is at, that's supposed to be a 3/4. I'm trying to save horizontal distance. 3/4 plus j 0.661. But do you see how you could find the value for that triangle, or that for that star, if you didn't want to calculate it? How far is this? We're on the unit circle. We're trying to find where star is. We know that it's on the unit circle, let's say. We know that we have a right triangle, and we know the horizontal leg of that is 3/4. And we know the hypotenuse, so we can solve for y. We know that x squared plus y squared is equal to 1 in this case. Since we're on the unit circle, we can solve for y. So now we can find some of these points maybe a little differently or better than we might be able to in the S-plane if we did it earlier. Yes? So now the question was, does that mean that we know the shape of the root locus? The root locus isn't going to curve any way. And in this case, since we have 2 real poles and only 2 real poles, we know that we're going to meet halfway between those 2 poles and then go vertical and not curve at all. We're just going to go straight up and down at plus and minus 90 degrees. So given that, that's what we're assuming, or that's what we're using to calculate that point star. Now that point star we just determined even without knowing what the k value was, but we could iterate on k, which is what we did here, and then if we wanted to, we could continually check the magnitude of that complex number and say, when is that magnitude equal to 1? If we didn't want to do that, if we wanted to just find where that star is located, we know it has an x value of 0.75. We don't know the y, but we know that x squared plus y squared equals 1. Question?
I think earlier you said that the exit point is the geometric mean of the two.
Okay, so the question was, I thought that you said the exit point or the breakaway point was the geometric mean of the two. Well, that's only when these guys are in the restaurant, when we have 2 poles and a 0. In this example, example 2 that I'm just now talking about, we just have 2 poles. They don't have a buddy. So because we just have 2 poles, we just have to worry about what's happening between them, and it's going to be equidistant between them. So you can see that things are a little different, which is good. That's why they pay us a little bit more than minimum wage. If we become an engineer and you've had this class, maybe you can convince others that there's some skill involved in figuring out how to design a controller that might meet the objectives that you're after. So that's why we're not using the geometric mean. We're using the average value that between this pole and the other pole. And that's why we're living at 3/4, which is half of 3/2. And what we were saying is this particular point, z star, was now 3/4 plus jy, but we know that 3/4 squared plus y squared must equal 1, and you can solve that for y. That's what I'm trying to suggest. Questions on that? And there's some commands if you want them for a particular calculator. Let's now look at a maybe more general case, suppose we now look at the following. Let's say we have a controller that has a gain K, and for whatever reason, let's just assume that you're okay with this controller structure, and this is why I'm calling it generalized notation. I'm basically trying to show you how we can extract the K or isolate the K and use that adjusting K strategy in our root locus sketch. But let's say this is the controller, and we now have a plant that is our G of Z. And what I'm suggesting now is that whoa. I have to watch, I have a heavy hand. What I'm suggesting for generalized notation is we put all of our pole and zero factors into a new block that we're going to call a G bar and just isolate the K so that we have the general structure for our sketching of the root locus. Meaning, now we can redraw this as if we had a K here, and now we had a Z here, and we have a Z plus 1, a Z, and a Z minus 2. So that this is now our G bar of Z, and we'll just collect the numerator and denominator together from whatever pieces we need, so that now when I start talking about root locus sketching, I've already done this. I've now put all of my numerator factors and pole factors together and just extracted the constant that I'm going to be varying. In this case, it's the K, from 0 to infinity. And what's the root locus look like for this example? Well, this one you can, I think, already see what the root locus is going to look like. But let's now look at the root locus for this system now that we've identified or incorporated our generalized notation. Now we have a G bar of Z that is now Z over Z, Z plus 1, Z minus 2. The Z's cancel. We don't need to worry about those two. And we now have 1 over Z plus 1, Z minus 2. So that now we can say, oh, we have a pole at -1 and a pole at 2. And what's the root locus look like? How many pieces of French bread do we have? 3. We're slicing it at 2 and at -1. Which of those 3 pieces or pieces belong to the root locus? Just the middle piece, isn't it? The piece between Z equal -1 and 2. This one's going to go right, that one's going to go left, and where are they going to meet? At the arithmetic mean between them. We have a distance of 3 separating those two poles. So they're going to break away halfway between that. So we're going to break away 1.5 to the left of 2 and 1.5 to the right of -1. Is that clear? So we're going to break away at 1/2. Question? When is it the geometric mean? Somebody want to help? That's when these guys are in the restaurant. So when we have 2 poles and a 0. In the one that I just sketched, after we looked at the generalized notation, we actually canceled a 0 at the origin with a 0 at the pole, so we don't need to worry about those. And now we have, for our transfer function, just a pure 2-pole system. 1 over quantity z plus 1 times z minus 2. So we don't have any 0. We just have 2 poles. And now we're going to be going straight up and down, and we will break away halfway between those 2 pole locations, which will be at 1/2. And now can you sort of tell me what might happen relative to this knob K in this system? How we might want to adjust it? Is it stable for all values of K? And what might we want to do? You actually might want to be sketching a unit circle. And you might want to know, okay, are both branches simultaneously inside the unit circle for certain values or ranges of K? And I hope you can see that at some point, as you crank up the gain K, the pole at 2 is going to go to the left, and it will start to come into the unit circle, and the pole at -1 remains inside the unit circle at that same value of K. And if I drew that, I might say, oh, here is where I am there, and now this one is going to be there. So as I crank up the gain K, I'm going to be just hitting the lower value of K at the square. And is there an upper value of K? Yes, and it's going to be right there, or right there. It's going to be the same value of K, and this Z delta is now 1/2 plus jy, and you know how to calculate y. And we also know that based on the magnitude condition, we know that needs to be 1. And we can use this to actually help us figure out what K is at various values of z. Or we now have K over the magnitude of z plus 1, magnitude of z minus 2, and I'm assuming K is greater than or equal to 0, so I'm just going to leave K outside the absolute value sign. And I now can say, oh, K is equal to z plus 1, z minus 2. And if I plug in a particular value of z, I can figure out what the K is to get me to that particular point. If I now want to know what's the K to get me to the square, what value of z would you use? So now I'm going to say K square. K sub square is, well, it's this expression for the magnitude of K when z is equal to 1, right? That's when I'm going to be right at the edge of stability. So now I have, this one's 2, and the magnitude of that one is going to be 1, since 1 minus 2 is minus 1. The magnitude of minus 1 is 1. The lower limit of stability is 2. So I need to crank up that knob k until I get to at least 2 in order to get me to that square, and then I can find the triangle point by solving for y. Since I know this distance, that hypotenuse is 1, I now know that I have a hypotenuse of 1 and a horizontal distance of 1/2. I can solve for y. That's 1 minus 1, the square root of 1 minus 1/4, or y is now the square root of 3. So the z triangle is now 1/2 plus j square root of 3 over 2. And if you plug that in for k triangle, do you see that the real parts are going to be the same? They're going to be 3/2. And then I'm going to have the square root of 3 over 2. And I think if you run through the numbers, you'll end up with k triangle being 3. So that's now our range of k for stability. If we get bigger than 3, we go unstable. Question?
So for a corresponding pole pair, like 0 and 1 in the box, does it matter which one we plug in?
So now the question was, which of these, if we know both locations, if we know both squares, we could plug in either value of z and get the same answer. Hopefully that's true. So if we plugged in z equal to 0, we get 1 times 2, or 2. And if we plugged in the triangle that was the conjugate of the one I plugged in, you better get the same k value. So it doesn't matter which of those points. Usually you just know one of those maybe. So you might know, oh, I'm coming in at z equal to 1. Let me plug in z equal to 1. That's why I did that one. But either one, as long as you know where they both are, if they are corresponding to the same value of k, then that's doesn't matter which one you use for z. What I'm trying to conclude with here in this example is we know that the stable values for k are between 2 and 3. This was k square and this was k triangle. Is that clear? So now we've actually done some controller design using this idea of generalized notation and knowing having some knowledge of a root locus shape. And this one was what? 2 poles. It wasn't 2 poles and a 0. It was just a pure 2-pole system. And we know that shape. That one should be locked in now for the remainder, actually, of your career. Not even this class. So even beyond May, let's say. June, you should remember this, okay? Now, all of these rules come from this very basic formula. And we now know that this expression leads to 2 conditions. We actually have k g bar of z equaling -1, but that's just 1 at minus 180 degrees. So if we keep k greater than or equal to 0, we know that the phase of g bar of z for any of these points on the root locus, those have to be minus 180, so that's the phase angle condition. And the other one is our magnitude condition, which is that the magnitude of k g bar of z needs to equal 1. Now let me give you a quiz again. Let's say here we are in the z-plane, and I'm just going to arbitrarily locate some poles and zeros. Suppose that I have a couple of poles here, and they have to appear as conjugates. Let's say I have a real pole here, and let's say that I have a 0 there, and I want to know what's the phase of this constellation of poles and zeros at that location. What's the phase at that starred location relative to all of these poles and zeros? If I said this is now my G bar, could you now determine the angle of G bar of Z? Somebody's been in a bar, I think, the way I'm stumbling around up here. I didn't think anybody saw that, but apparently I'm not quite that graceful. Stumbled into the podium. One professor walked into a podium. What happened? What's the angle? So what's the angle here? How do we find it? We just measure it with a protractor. If all of these angles, or if all of these distances were correct, we have this angle, we have that angle, and all of these angles are measured with respect to a positive real line extending to the right. Let's say I call this theta P1. I call this theta P2. This angle is theta P sub 3, and this angle is theta Z. So that the phase of G bar of Z, when Z is equal to that star, that's going to be the angle of the 0, theta sub Z, minus all of the angles from the poles. Theta P1 plus theta P2 plus theta P3. So now I just ask you to compute the phase of that collection of poles and zeros. You could do that, but now maybe somebody says, well, is that star on the root locus? Suppose somebody's now calculated this algebraic sum of angles. Could you now tell them, is star on the root locus? And how would you determine that? Is this an easy question to answer? If you've now computed this angle from the net angle, the algebraic angle from the sum of these four, the algebraic sum of these four, what are you really looking for? One option would be if the angle of G bar of Z was equal to minus 180 degrees, what would you say would be your answer to that question? Is star on the root locus? Yes, thank you. Didn't take you to stumble, did it? So now if the angle of G bar of Z was not equal to minus 180, then how would you answer? Hopefully it would be an emphatic no, right? So now you're really just looking at the angle. If you were needing that much to do and you were poking around and saying, okay, I'm going to put a star here and let me calculate the angle, Then let me put a star here. You're guessing where the root locus is. That's a slow process. You don't want to do that. But now if somebody just gave you a z location and said, is this z location on the root locus? Do you see how you could make that determination and it wouldn't be too difficult? You just need to find all of your angles, compare or add them up algebraically, and see if their angle sums to minus 180. I actually was hoping to get through this, which are 3 rules. So I've already written them down, so I just have to read them in 2 seconds or something, maybe. Can't see the time, but here's rule number 1. We've already talked about this. The root locus branches begin on the open loop poles. Those are the roots of d of z in the generalized notation, and this will be a part of the notes, so you don't have to write it down, just absorb it. And the root locus branches end on the open loop finite zeros of g of z. But we may have more poles than we have finite zeros, and if we do, then those zeros at infinity are where the other branches approach. That's rule number 1. That's just kind of the overall picture. Rule 2 is our French bread rule. Which segments of the real axis belong to the root locus? If we have an odd number of poles and zeros to the right, then that segment is on the root locus. That's rule 2. Now, if we have, what I want you to make sure you're clear on is we could have a real line segment that has multiple branches of the root locus on it. That line segment here contains 2 branches of the root locus. Even though it's one segment, we have one pole going from the pole on the right and another closed loop pole coming from the pole on the left. So we have 2 poles, and they will meet in the middle. So breakaway points and reentry points, they break away when these 2 meet, and that may vary from just the algebraic mean, depending on how many poles and zeros we have. And we'll calculate the relative maximum of the gain value. We figured out a gain expression in one of our earlier examples. That might get more complicated later, but we can figure out where's the relative max and relative min of that k expression. Use that to figure out where we break away and where we re-enter the real line. Those are the 3 rules that we need to get under our belt for exam number 3. We'll pick up at this point. Oh my, thank you for being patient. Later.